Hello and welcome to the second video for differentiation for the second year maths content. What this video is going to focus on is looking at exponential differentiation. So, first off, looking at y equals e to the x and this kind of thing. This was covered in the first year textbook or the first year content. So you should remember the point of this function is that the gradient is the same as the function at every single point. And in a similar way, if we have a number here, that number sticks on the front and we get there. This is a very, very similar property or similar rule to the trigonometry in the previous video when we had things inside our function. This idea of the kx here, the k jumping on the front and everything else sort of behaving as we'd expect, is a common theme. And it's something we will get to in another video when we look at the chain rule. But that's for a later video. So let's do a couple of examples. So find dy by dx when y equals 3e to the x, y equals e to the 2x, y equals e to the minus 4x, and then y equals 2e to the x plus 1 over e to the x. Okay? If you're confident with these, then pause the video and have a go yourself, and then come back when you're done to have a look at my answers. So here, this one, we've got nothing in the power, or just an x in the power, which means the e to the x bit behaves in this way. The 3 on the front just stays there. This second example follows this rule. Notice how we have 2x in the power. So the 2 is going to jump down to the front, and then everything else is going to stay as it is. Remember, this idea of things staying as they are is exclusive to exponentials, or e to the power of stuff. Here, this one's going to work in a very similar way. Minus 4e to the minus 4x. Now this last one, part D, we're going to have to do a little bit of rearranging first. This first function, we're going to have no problem with that differentiating. It's this bit that's a problem. Our rules only work when we've got e to the power of something. This is 1 over e to the power of something, so we need to deal with that first. And this uses those laws of indices from GCSE and the Year 1 content. So the 2e to the x, that just stays as it is. Remember, we haven't differentiated yet, so it's still y equals. 1 over means we change whatever power this is to a minus. Now we've got things in the form e to the power of stuff we can differentiate. This first function behaving exactly like part A, just with a 2 instead of a 3. This one, so we now have minus 1 in our power. So the minus 1 goes on the front, and then everything else stays the same. You may want to as well put this into the form of the original question, but this is probably sufficient. But what happens if our base isn't e? If it's some number, so something like 2 to the x, for instance, or 10 to the x. Well, we can use the property we've just looked at to figure out what the derivative of this is. So, we have y equals a to the x. So what we can do is we can think, okay, we know how to differentiate e to the power of something. So how can we write this as e to the power of something? Well, we need, because we don't have an e here or anything else, we need to think of what would we do to cancel out the e's? Well, if we have e and a ln next to each other, those cancel out, just leaving the function in there. So, if we stick a ln on the front of this, and then raise that to the power of, to do e to the power of that, we end up with the same thing. So this is a rule you can always do. It doesn't have to be with powers, but this is typically how we use it. Now, don't forget, we know how to differentiate things of the form e to the power of some number times x. That's not what we've got here. So we need to rearrange this power to make it look like that. And we do that by using our laws of logs. Remember, a is a number. Which means ln a is a number. So if we think about the e to the 2x we had in the previous example, that differentiated to 2e to the 2x. This is going to behave exactly the same way. We're just replacing the 2 with ln a. So we have x times a number. The number sticks on the front. The rest of it all behaves as normal. We now have to get rid of or to simplify this bit. And we do that by doing this process backwards. And then just to make it look more, look nicer, the e and the ln cancel out, just leaving a to the x, which is, as we saw here, just in reverse. But just to make it read nicer, I'm going to stick it on the front. You need to learn this proof. This is something you might be required to do in the exam. So, in general, if y equals a to the x, then the derivative is a to the x ln a. So for instance, with this example, with the first example that I kind of talked about, 2x, the derivative would be 2 to the x ln 2. And that's it. Unless you're asked to prove this relationship, to prove this, you can just use this like I did here. But if you are asked to prove or to show that the derivative of a to the x is a to the x ln a, this is what you need to do. There is another way to do this example that you can kind of figure out later on when we look at something called implicit differentiation, but this is the more traditional way to do it. This is the simpler way to do it. And that's it for exponential differentiation. In the next video, we'll look at logarithmic differentiation as well. Thank you for watching.